All right, our next speaker is McKenzie Larson, coming to us from the University of Colorado Boulder. McKenzie will talk about future changes to extreme downslope windstorms across the northern Colorado Front Range. Thank you.
Perfect, thank you. Hi everyone, so I'm McKenzie Larson, she, her. I'm about to start my 5th year of my PhD at the University of Colorado in Boulder. Today I'm going to present some of my PhD research with my advisor, Andrew Winters, as well as some collaborators at the National Center for Atmospheric Research, or NCAR. Those are Jerry, Christine, and Aaron. So let's get into it. So to start off with, what is a downslope windstorm? A downslope windstorm is a really strong, gusty wind that blows down the leeward side of a mountain range that looks something like this. It often weakens. You have the strongest mountains right at the foot of the mountain, and it rapidly weakens as you move further away. And we care about these downslope windstorms because they damage property, or they endanger lives, they damage property, they disrupt travel, and they also exacerbate fire weather. So one recent example of a downslope windstorm that you might have heard of because it made national news was the windstorm associated with the Marshall Fire that occurred near Boulder, Colorado on the 30th of December in 2021. This was a day where we had a really strong downslope windstorm, gusts going up to 100 miles per hour, really just persistent for hours. It was also very dry, and there was a fire that started during this windstorm, which made it extremely difficult to stop. Throughout this fire, there were over 1,100 homes destroyed, just outside of Boulder and Denver, 2 deaths, and the peak gust actually measured in Boulder at the NCAR Observatory was 112 miles per hour. So these are some strong winds. You're getting into like hurricane force winds. And so specifically in Colorado, we have 2 flavors of downslope windstorms. The first are going to be Chinook or Föhn winds. And these are our warm downslope windstorms. So these are what we usually get when you have a low pressure system that you can see up here over the central US before a cold front has moved through and reached Colorado. We're usually getting winds coming from the west or the northwest. And so schematically, if I made a slice like along the Rocky Mountains, it would look something like this. You have some cold air that's dammed or trapped behind the mountain range, and that allows this warm air aloft to essentially skate along the surface. It reaches the top of the mountain, and then it descends down towards the surface. And as this air descends, it speeds up. It also compresses and warms, leaving you with really fast, warm, dry air at the surface where we all live. Another way you can get a Chinook wind is through something called orographic precipitation, or you might know it more as the rain shadow effect. And this is where you have really moist air that runs into a mountain. It needs to rise. The water vapor all condenses, it precipitates out, leaving you with really dry air that then descends down towards the surface and continues to speed up. But for today's talk, I'm going to be focusing on the other type of downslope windstorm we have in Colorado, which is called a Bora. So these are now going to be our cold downslope windstorms. So this is once we have a low pressure system move through and the cold front has already gone through Colorado. That's when we expect to see these Bora winds. And we're usually having winds coming from the northwest. So instead of having this air, like in the Chinook case where it was trapped behind the mountain, now you have this depth of cold air that now exceeds beyond the height of the mountaintops, but it's capped by this warm layer aloft. So you have this really stable layer at the top of the mountains. So when this cold air, runs into the mountains, it's forced to rise, it only has this really shallow depth to move through. So it needs to speed up by Bernoulli's principle. So the air is funneled upward, speeds up at the top of the mountain, and then it also continues to speed up as it descends down towards the surface. So now that you know that these downslope windstorms are impactful, you know how they form, I'm going to talk to you about my research question as part of my PhD, which is to specifically look at how an observed windstorm could change in a future climate. So the specific observed downslope windstorm we're going to look at today is from the 15th of December, 2021. So this was the windstorm we had before the Marshall Fire, and it's a Bora, so it's one of the cold downslope windstorms. The National Weather Service was issuing high wind warnings, expecting for pretty much all of northeastern Colorado 60 to 80 mile per hour wind gusts, but especially along the Colorado Front Range, you're expecting gusts up to 100 miles per hour. So during this windstorm, there were big trucks turning over, lots of dust, power lines going down, very, very impactful. So to actually look at this storm a little more, we're going to get into some weather maps. So this windstorm occurred from 14 to 22 UTC, which is Universal Coordinated Time. That's roughly 7 a.m. to 3 p.m. Mountain Time. and it's associated with a cold frontal passage. So on the right, I'm going to walk you through this weather map. So this is at 14 UTC. In the black lines, you're seeing mean sea level pressure. The little barbs show surface winds, and then the blue and red contours show the cooler and warmer 700 hectopascal temperatures. But what I want to draw your attention to is that this is right at the start of the windstorm. You have this low pressure system situated over southeastern Wyoming. And what's really important is that this cold front that is moving through is essentially parallel with the Rocky Mountain range. So it allows for us to get this really nice cross barrier flow as the air moves through. So to look at this windstorm a little bit further, I'm going to use a model. And here that's going to be the Weather Research and Forecasting Model, or the WRF model. These are what my domains for these simulations look like. I had 3 domains. You have the first outermost 9-kilometer domain, which is over a good bit of the central United States. From there, one of the nested domains is 3 kilometers. It covers the entire state of Colorado. And then I have a 1-kilometer resolution domain in the middle that is blown up here on the right that extends along the entire northern Colorado Front Range. And on the right, too, you're seeing maximum wind gusts in the little circles at different observation sites along the Colorado Front Range. So these dark purple dots are showing where you had over 30 meters per second winds. And specifically throughout this talk, I'm going to mention this Colorado 109 site that's denoted with this little star on these plots. And that is a well-known observation site to capture these downslope windstorms by the Weather Service. So a little bit more about some of these weather simulations. I gave them 12 hours of spin-up time, along with having really nice horizontal resolution, fine resolution going from 3 to 1 kilometer. I also wanted to have quite fine temporal resolution, so I produced 5-minute output to better match the 5- and 10-minute observational data that we're gathering along the Front Range. We're using ERA 5 initial conditions, which is just a commonly used data set in the atmospheric science field. It is quarter degree by quarter degree horizontal resolution. And then if anyone really wants to dive into more of the nitty gritty of what I specified in this model, I'm happy to answer questions about that, but I'm not going to do that here. So now we know how we can model this windstorm, but how can we actually look at it in a future climate? And so the way to do this is through something called the pseudo-global warming approach, or the PGW approach. And this is where you impose large-scale changes in the climate system onto a regional climate model. And you do this by changing the boundary conditions. So the large-scale changes here are going to come from the Community Earth System Model version 2 large ensemble, or the CSM Lens 2 data set that's developed at NCAR. We're going to be using all 100 members, and specifically the wintertime data. And then those large-scale changes from the Lens 2 are going to be imposed onto the regional simulation, WRF, which we just talked about. So the way that this works is you calculate these future climate anomalies, or these little deltas of the Lens 2 data. You calculate that by taking a future time period, subtracting from that a historical time period. You do this for pretty much all of the variables WRF needs to run. So 3D variables such as temperature, moisture, going into surface variables as well. So things ranging from sea surface temperature to different soil temperatures and different layers of the soil. But I'm going to do this for each of the 100 Lens 2 ensemble members. From there, you take these little anomalies from Lens 2, you interpolate them to match the WRF initial condition data, which is that ERA 5 data set. You just add them together, and then you run your WRF simulation, and that gives you your PGW WRF simulation. So a representation of how this 15th of December windstorm could look in a future climate. And then I'm going to run this 100 times to get a good bit of variability of a sense of how these windstorms could look different with the different climate variability we have as well. From there, I'll also compare it with a control ensemble where you're calculating historical mean deviations in the Lens 2 data set. So you take the historical time period that we talked about, subtract from that the historical mean. You take these deviations, again, you interpolate them, you add them onto the WRF initial condition data, you run WRF again, and that gives you your control WRF run for the windstorm. And again, you do this for all 100 Lens 2 ensemble members. So this is a lot of modeling, so it takes some good high-performance computing to do that. So when I have, this downslope windstorm simulation, I have 3 domains, 2 of them have 5-minute output, you're going down to 1 kilometer spatial resolution. It's a lot of data, and then I also do that 200 times. It's giving you about 45 terabytes of output data just for about a 22-hour model run. So it's a lot of data. So I was very thankful I was able to use the derecho supercomputer at the National Center for Atmospheric Research. They have a lot of the data that we need to run these models, as well as the storage to hold all of this. So now that we've talked about how this all works, let's dive into some results for the last little bit. So again, we're going to start at that Colorado 109 observation site that had the little star on the map. We're going to look at how the 10 meters, so just like the surface wind speed, is modeled in both the PGW simulations, that's shown in the blue line here, the average, and then in the control ensemble as well, the average is shown in the black line, and then its observations are shown in the red solid line, and then for wind speed, and then the wind gusts are in the dashed red line. So you're going from the start of the windstorm at 14 UTC to near the end of the windstorm at 0Z. So you can see, if we just look at it kind of from far away, at the start of the windstorm, as it progresses, the model is following a really nice evolution of the windstorm with what we'd expect to see in observations. But what I want to talk about for the rest of this talk is what's happening a bit later. So specifically, you compare the PGW blue line to the black control line. The way that they're ending the windstorms are different. So it seems like the average PGW in the future, so the future climate simulations are actually shortening the duration of this windstorm. It's ending about an hour too early. So we're going to dive into that. We want to see, why is the PGW duration shorter than the control simulation? So we're going to start by looking at some more weather maps. This is at that 22 UTC time, so right when the windstorm's kind of starting to stop in that future climate simulation. On the left here, you see ERA 5 reanalysis. So it's like our best guess at like a observational data set. It's also what was input into WRF. We can see that we have nice zonal flow over Colorado. So we're getting that flow coming from the west. Specifically gives us that good cross-barrier flow. The faster wind speeds, these are at jet stream level, so pretty high in the atmosphere, 250 hectopascals. Those faster wind speeds are going to be in the purple. So we're having these really nice fast wind speeds over Colorado. But if we actually look at what's going on in the WRF simulation itself, on the right here, you have the 9-kilometer outermost domain of the WRF simulation. On the left is that average PGW, and on the right is control. And so they both have this flow coming from the west, the wind's moving from the west, but the big difference is that in this PGW simulation, you're seeing a lot more purple. There are much faster wind speeds associated with the jet stream, or what we'd call this little fast part is called a jet streak, that is occurring over Colorado. So that's going to have some impacts that I'm going to walk you through here. We're going to start by looking at a cross-section of wind speed along that Colorado 109 latitude, so it's going to span the entire state of Colorado, like you can see on the right, from A to A prime. And so on the left, again, that's that cross-section. Higher wind speeds are in purples. The potential temperature lines are in black. And so we're looking for that stable layer, which is when all the black lines are nice and close together. So I'm going to let this play. It goes from the start of the windstorm at 14 UTC to the end at 0 UTC. And there's two features I want to point out. You can see, the jet stream aloft. That's what we just talked about on the last figure on the last slide. So we have these fast wind speeds above, but you can also see this trapped bit of purple down here. So that's the downslope windstorm, where you can see the winds descending down on the leeward side of the mountain. Now, to better actually compare how this looks different in those PGW simulations, we can take PGW minus control. So here, if there's an increase in wind speed in those PGW simulations, that's going to be shown in red, but a decrease will be in blue. And there's a lot to see on here, but I'm going to point out one major feature, which is going to be this big red blob that's moving through. And so like we talked about on the last slide, when we were looking at more from a top down, we saw those increased high wind speeds. That's what we're seeing here. So that's a major change. These are nice big red values at 18 meters per second. Those are some fast winds that have now been introduced into this downslope windstorms dynamics. So if we take a little kind of slice through time, we look at 19 UTC, so that's about 3 hours before the PGW simulation starts to stop the windstorm. We can really see that we have a good bit of air above that is increased in the PGW simulation. So if we kind of look at this a little bit schematically, when we talk about downslope windstorms, we're thinking a lot about what's happening at mountaintop, what's happening above mountaintop. And so what's happening here is we're having increased wind speeds above mountaintop, and then we're also getting increased wind coming from above. So you have a lot of subsidence or downward vertical motion happening as well. And that also brings dry air with it. So to just kind of summarize what I'm working on, I'm still trying to figure out what's all going on here. It's very complicated and very interconnected. But we believe that the increased jet streak wind speeds in the PGW simulations are likely resulting in increases in the vertical wind shear, which downslope windstorms are extremely sensitive to. Also, this subsidence and downward vertical motion can move the stable layer and the depth of the stable layer that we need to have this downslope windstorm. It's also introducing dry air as it comes down as well. So that's all gonna have impacts probably on latent heating and many things that all talk to each other. So this is what we believe is impacting the duration of the windstorm. And so with that, I wanna thank CSGF and Krell and everyone for everything. It's been awesome.